Hi, my name is George Diamond, and today we're going to look at some examples of using the product and quotient rules for derivatives. We'll look at a bunch of examples today of how to use the product and quotient rules to find the derivative of functions that have multiplication and division in them. Start off with our first example. We're going to find the derivative of each. Start off with h of x equals the quantity 3x minus 2x squared times the quantity 5 plus 4x. Now, immediately you recognize this is a product. Now, some products are a little bit harder to recognize than others. Now, this one is easy. You have two polynomials being multiplied together. Now, if you remember from our previous video, we said according to the product rule, as you take your derivative, you go take your first function, 3x minus 2x squared, times the derivative of the second, which is 5 plus 4x. So the first times the derivative of the second, plus the second, which is 5 plus 4x, times the derivative of the first, which is 3x minus 2x squared. So once again, the first function times the derivative of the second, plus the second times the derivative of the first, and this will give us an expression for our derivative. Now, a lot of times, getting the derivative is the easy part. I always thought when I took calculus, simplifying the expression was a lot harder, in some cases much harder than actually getting the derivative itself. This is where our algebra skills are going to come in. So let's get our derivatives here. So they describe our derivative. We'll bring the first function, the first product down, so it'll be 3x minus 2x squared. Now the derivative of, as you take the derivative of 5 plus 4x, now you got to remember you're using the sum property here. The derivative of 5 is 0. The derivative of 4x is 4. Plus. So that's the first times the derivative of the second. Okay, plus the second, which is 5 plus 4x. Okay, now once again, as you take the derivative of what is the first function here, 3x minus 2x squared, it's a polynomial. As you take the derivative now, we're going to take the derivative of each part. The derivative of 3x is 3. Okay, minus, now as you take the derivative of 2x squared, we're using the power rule. 2 times 2 gives you 4x. Now, this is an expression for our derivative. Okay, now let's see if we can simplify it, all right? So like I said, simplifying is a lot of times is harder actually than getting the actual derivative. This is pretty easy. Okay, now that means removing parentheses, combining like terms if you've got them, and then we'll go ahead and simplify from there. So let's multiply 4 inside our parentheses here. Will give us 12x minus 8x squared. Okay, plus, now as we multiply here, we'll use the full method to multiply. 5 times 3 will give us 15. 5 times negative 4x is negative 20x. 4x times 3 gives us 12x. 4x times negative 4x gives us negative 16x squared. All right. Now that removes our parentheses, so we've got all of our multiplication done. Now let's go through and combine like terms if we have any. Now immediately you recognize we have a couple, well, no, not there. We do have a couple of x terms, or a couple of x squared terms. We'll combine those two. That will give us negative 24x squared. Now we have a couple of x terms. So let's see. 12 and 12. 12 and 12 is 24 minus 20 gives us plus 4x. And then we've got what, the 15. And that's our only numerical term we have. We'll bring that down. And this is our derivative. So h prime x is equal to this right here in simplified form. And like I said, the actual derivative is pretty easy. The simplification can be harder than the derivative. Let's try another example. Now we'll be moving through these pretty quickly, so just kind of keep up. So as we get started here, we've got 2x cosine x minus sine x. Now as we find our derivative, I said for a lot of students it's kind of difficult sometimes to see where the product is. All right, now this is a trig function, so as I look at this, you got 2x cosine x. Now you got to recognize that this first term here, that's a product. You got 2x, so I'm going to put parentheses around the 2x. That's a linear function times cosine x. Now cosine x is a trig function. Now this right here is a product. Okay, that's a product. Now 2 sine x is kind of a product also, but now 2 is a constant. So we don't need to use the product rule to do 2 sine x. Right? But now 2x cosine x, you got to use the product rule. So, let's see what we get. Now we set this up. So we'll take, as we describe our derivative, y prime will be equal to, now 2x cosine x, 2x is the first term, cosine x is the second term. So this will be 2x times so the first term times the derivative of the second, okay, plus the second, which is cosine x, times the derivative of the first, minus 2 times the derivative of sine x. So as you set this up, this is the way it's going to go. Now to get our derivative, so the first times the derivative of the second, plus the second times the derivative of the first. Now that's the product rule. Then minus 2 times the derivative of whatever sine x is. Now if you remember, the derivative of cosine is negative sine, so finding our derivative here. So let's make this negative 2x sine x. So we'll just bring the negative out front. Okay, plus, now the derivative of 2x is 2, so we'll put the 2 out front here, in front of the cosine x. How's that? And the derivative of sine is cosine, so it'll be negative 2 cosine x. Now, there's your derivative. Now, like I said, you got to simplify it if you can, all right? So some of these trig functions, they'll simplify several times sometimes. So looking at any like terms, now I notice immediately now we got 2 cosine x minus 2 cosine x. Well, those two add up to 0, so those are gone. That leaves us with negative 2x sine x. That's our derivative now. So negative 2x sine x. Let's try another one. Let's try 2 more polynomial functions, right? Now, as you multiply, now immediately you recognize this is a product. So these two here are being multiplied. So you have a trinomial times a binomial. It's easy to recognize that product. Like I said, especially with trig functions and things like that, it can be kind of hard to tell that you actually have to use the product rule. In this case, it's easy. We're going to have to use the product rule here. So as we describe our derivative now, this will be the trinomial will be our first term. So this will be x squared minus 2x plus 1. So the first times the derivative of the second. Now I'm going to go ahead and write the derivative down this time. So we should know how to find the derivative of x cubed minus 1. This is the difference. The derivative of x cubed is 3x squared. That's the first times the derivative of the second plus the second, which is x cubed minus 1, times the derivative of the trinomial. Now take the derivative of the trinomial. We're going to take the derivative of each term. The derivative of x squared is 2x. The derivative of negative 2x is minus 2. And the derivative of 1 is 0. Now this is the derivative. Now we get to simplify. So let's see what it'll simplify to. Now this will simplify as, we just have to use our distributive property, multiply inside of our parentheses here, which is 3x to the 4th minus 6x cubed plus 3x squared. Now you got to be careful with the multiplication and stuff. Multiplying the 2 binomials, let's use the full method to multiply the 2 binomials here. This will be plus x cubed times 2x will give us 2x to the 4th. Multiply the outside terms, x cubed times negative 2 is negative 2x cubed. Multiply the inside terms, negative 1 times 2x is negative 2x. And multiply the last terms, negative 1 times negative 2 is 2. All right, now hopefully I did all that correctly. All right, so you got to be real careful with your signs, with your multiplication as you're multiplying here. Now last, we've done our multiplication. All we have to do now is combine like terms now. We've got a couple of x to the 4th power terms. We'll multiply, we'll add these two together. That gives 5x to the 4th. A couple of x cubed terms, negative 6x cubed and negative 2x cubed is negative 8x cubed. Plus 3x squared and minus 2x squared will give us a positive x squared. And then I believe we only have the one x term, so minus 2x plus 2 bring down. All right, so that should be our product right there. Okay, so this should be our product. Let's try another example. Let's see how we go about using the product rule to find this derivative. So actually, any fraction, you can write it as a multiplication. Now, on our other video, our previous video, we looked at using the quotient rule to get this derivative. So you already have this in your guided notes. So let's see if we can use the product rule to find the derivative here. Now let's rewrite this. Now to use the product rule, I'm going to pull this x off as x to the negative 1 times sine x. Now you have a first term times a second term now. Now let's use the product rule. Now you can actually do this to any fraction. Sometimes it may make it a little easier to find the derivative of, a lot of times it don't. But just to kind of see what this will look like as we find our derivative. So using this time we use our product rule. So the first time derivative of the second, the derivative of sine x is cosine x. This will be x to the -1 times cosine x plus, so the first time derivative of the second plus the second, which is sine x, times the derivative of the first. So the first derivative of the second plus the second times the derivative of the first. Now the derivative of x to the -1 is negative x to the -2 power. Now we don't want to leave that negative exponent there, so let's see if we can get rid of these negative exponents. And this will be cosine x over x, actually minus, this will be minus. Because of the negative, we'll pull the negative out front here, and this will be sine x over x squared. Now you can actually combine these to make one big fraction, and it'll look like the one that we did earlier on the previous video, but I'm going to leave it here because I want to move on. Okay, let's try this example here. Now we're doing sine x cosine x, and as we find our derivative this time. Now this is easy to recognize that we have a product. You know, sine times cosine. This is easy to recognize. So as we set it up now using our product rule, as we get our derivative, f prime x, this will equal to the first times the derivative of the second, okay, plus the second times the derivative of the first. Now, so the first or the second plus the second derivative of the first. So we get our derivative then. The derivative of cosine is negative sine. So we end up here with negative sine x times sine x. Now we'll pull the negative out front. So it makes that a negative sine x plus, now the derivative of sine x is cosine x. This will be cosine x times cosine x. Okay, now that's our derivative. Now we go and to simplify, let's multiply sine and sine, cosine and cosine. This will be negative sine x, sine squared x plus cosine squared x. And there you go. Now I'm going to leave it like this. You can still simplify it a little bit further, I'm sure, but once again, I want to save a little bit of time. Now look at number 6. Now a lot of students, when they see number 6, they won't see the multiplication. Okay, if you're not watching for it, this type of problem is easy to recognize that you're going to have to use the product rule to take a derivative of this function. Now cosine x is okay, but when you look at x sine x, x is your linear function times a trig function. So we're going to have to use the product rule to take the derivative of x sine x. So let's see what we get. Okay, the derivative is. Now the first function is x, the second function is sine x. So it'll be the first times the derivative of sine x, which is cosine x, plus the second, which is sine x, times the derivative of x. So the first derivative of the second plus the second derivative of the first, which is 1. So the derivative of x is 1. Okay. Now the derivative of cosine is negative sine. So let's go ahead and take the derivative of cosine x. That'll be minus sine x. Right, so x times cosine x plus sine x times 1 minus sine x. Now let's see if we can simplify this a little bit. This will be x cosine x, okay, plus sine x minus sine x. Now, immediately I recognize we got sine x and minus sine x. These two add up to 0. All right, this will just give us x cosine x for our derivative. So the derivative is y prime is equal to x cosine x. The two sines, sine x is canceled out. Let's try another example. Okay, this says use the quotient rule to find the derivative of each. So this time, let's try the quotient rule. We did several examples just now of the product rule. Okay, this is the first one on this video that we've used the quotient rule with. Now, if you remember the quotient rule, it says if you're given, let me just once again just refresh everyone's memory. We'll erase this here in just a second, but if you're taking the derivative of f of x divided by g of x, okay, according to the quotient rule, we take g of x squared. So you take the bottom of your fraction and square it. All right? And then in the numerator, now with the quotient rule, you got to be very careful because it has subtraction in it. Subtraction, you cannot change the order. If you do, you miss it. So in the numerator, you take the bottom of the fraction, g of x, times the derivative of the top. So the bottom times the derivative of the top minus the top times the derivative of the bottom. So times f of x times the derivative of g of x. So this is the quotient rule. This is what we're going to use here. Now, we looked at this in our last video, so if you're one of my students and you have the guided notes, you should already have this down. So let's take a look at this example here, and let's see if we can get the correct derivative now. All right, so let's see if we got the correct derivative. All right, so as we set this up, all right, this will be here we go. Okay, this will be the bottom squared. So the bottom of your fraction here will be x squared plus 1 quantity squared. So take the bottom of your function squared. Now in the numerator we'll take the bottom times the derivative of the top. So it has to start off x squared plus 1. So the bottom times the derivative of the top, 5x minus 2, minus the top, which is 5x minus 2 times the derivative of the bottom, which is x squared plus 1. All right, so as we set this up, this is the way it's going to set up. So the bottom squared, and then the bottom times the derivative of the top, minus the top times the derivative of the bottom. Now let's go ahead and actually take the derivative here. Let's see what we get. On the bottom we still have the x squared plus 1 quantity squared. Now bring the x squared plus 1 down. The derivative of 5x minus 2. Now that's a difference. We should be able to find the derivative of that little binomial. You've got to take the derivative of each part. The derivative of 5x is 5, and the derivative of negative 2 is 0. So remember, the derivative of any constant is 0. Okay, minus. Now you got to kind of watch out. So I'm going to put some grouping symbols here. Let's bring the 5x minus 2 down. Okay, times the derivative of the bottom. Now the derivative of the bottom is x squared plus 1. The derivative of x squared is 2x. And the derivative of 1 is 0. Right, so this is the way so this right here is our derivative. So that's it. Right, so we've got our derivative. Now the hard part starts. Now we get to simplify the expression. So simplifying, we're going to have to, in the numerator especially, let's multiply, combine like terms, and then see if we can do anything else. So multiply 5 inside your parentheses, we get us 5x squared plus 5. Now, here's what you got to watch out, because you got a negative in front of your parentheses and the 2x, both of these being distributed inside your parentheses. So as you multiply, 2x times 5x is 10x squared. The minus sign makes it a minus 10x squared. You see this? Now that's where you got to be careful, because this minus sign out in front of your parentheses. So the 2x times 5x makes it a 10x squared, and then the minus sign makes it a negative 10x squared. Now, 2x times negative 2 makes it a negative 4x. The minus sign makes it plus 4x. That's our numerator now. Right? All this divided by x squared plus 1 quantity squared. Okay. Let's extend our page here a little bit. Now, combining like terms, we've got 5x squared minus 10x squared is negative 5x squared. Plus 4x plus 5, all that divided by x squared plus 1 to the second power. Now this is our simplified derivative. I don't think it's going to simplify any further. That should be it. But like I said, actually getting the derivative itself isn't that hard, really. Right? It's just simplifying, watching that minus sign. So watching this minus sign, you've got to be very, very careful. Typically, with my experience, the student misses the quotient rule. They know what they're doing. This minus sign right here can cause them to miss the problem, so be very careful. Let's move on. Okay, let's try problem number 8 now. We got, this is 2 polynomials, polynomial division. We're going to use the quotient rule to take the derivative. We got x cubed plus 3x plus 2 divided by or over x squared minus 1. So let's see what we get for the derivative here. Now, so set this up. Y prime is going to be equal to, now the bottom, which is x squared minus 1 squared. Now remember, in the quotient rule, you got to be very careful as you set this up. So it'll be the bottom minus 1 times the derivative of the top. Now as you take the derivative of x cubed plus 3x plus 2, the derivative of x cubed is 3x squared. The derivative of 3x is 3, and the derivative of 2 is 0. So that's the bottom times the derivative of the top minus the top, which is x cubed, plus 3x plus 2 times the derivative of the bottom. Now the derivative of x squared is 2x, and the derivative of minus 1 is 0. All right, so this right here is our derivative. Now we get to simplify it. So let's see what we get when we simplify this down. Okay, in our denominator, this is still x squared minus 1 quantity squared. Now you got to use your full method to multiply the two binomials. X squared times 3x squared gives us 3x to the fourth. X squared times 3 gives us a positive 3x squared. Negative 1 times 3x squared is negative 3x squared. And negative 1 times 3 gives us negative 3. Okay, so that multiplies our full method. So x squared times 3x squared is 3x to the fourth, plus 3x squared minus 3x squared, and then minus 3. Now, once again, be very careful with the next distribution. Let's multiply. We've got to multiply 2x inside our parentheses. So once again, just using our distributive property. We're also distributing the negative at the same time, so you've got to be very careful here. So 2x times 3x squared is going to give us 2x to the fourth power. Then the minus sign is going to make that a minus 2x to the fourth. So distribute that 2x to the x cubed. 2x times 3x is 6x squared. We'll make that a minus 6x squared. And then 2x times 2 is 4x. And then the minus sign will make that a minus 4x. Okay. Now we got our multiplication done. All right, so if we did everything correctly, you got to watch out. Now right away I noticed that the 2x squares here are going to cancel. We have, as we simplify here, so the x squared minus 1 quantity squared still. Let's see, now we have a couple of x to the fourth terms. So 3x to the fourth minus 2x to the fourth is going to give us x to the fourth. Let's see what's left. Now we've got a minus 6x squared. We'll bring that down. Minus 4x. All right, we only have the one 4x term. I don't see any others. And then the minus 3, we'll bring that down. This should be our derivative now. Now we got it simplified. Like I said, the actual derivative a lot of times is pretty easy, and then simplifying it, you got to be very careful. There's a lot of opportunities here. Just a missed sign will cause you to miss the entire problem. So you got to watch out. Let's try another example. It says determine the point at which the graph of a function has a horizontal tangent line. Now you can imagine, if you can imagine the graph, if you look at a graph that has a horizontal tangent line, okay, this would be a horizontal tangent line. The graph of, or the slope of any horizontal line is 0. Okay, that means that the derivative is also going to be equal to 0 too. So you want to keep that in mind now as we look for a point at which the function has a horizontal tangent line. So as we get our derivative here. Right. Let's start off, let's get our derivative. Remember, the derivative is a slope. So once we can get our derivative expression, I know that the derivative has to be 0, so we're going to set it equal to 0, and then from there we'll see what we get. Now let's describe our derivative here first. So we set this up. So f prime x is going to be equal to, and this will be x squared plus 1, quantity squared in your denominator, so remember the denominator squared. And we start off in the numerator, this will be the bottom, x squared plus 1, times the derivative of the top. And the derivative of x squared is 2x. Okay, minus, so the bottom to the top minus the top, which is x squared, times the derivative of the bottom. Now the derivative of x squared plus 1, now the derivative of x squared is 2x, and the derivative of 1 is 0. So this here should describe our derivative. And once again, the bottom squared, so x squared plus 1 quantity squared, and at the bottom, x squared plus 1 times the derivative of the top, which is 2x minus the top times the derivative of the bottom. And just be careful as you take the derivative of the denominator. The derivative of x squared is 2x. There, you got it. Now let's see if we can simplify this a little bit. And then this will be x squared plus 1 quantity squared. Now multiplying 2x inside our parentheses will give us 2x cubed. 2x times 1 will be plus 2x. Multiply 2x to the x squared will give us a minus 2x cubed. Now combining like terms, let's see, now we got a couple. Now these two here will add to 0. That will give us what? 2x over x squared plus 1 quantity squared. So x squared plus 1 quantity squared. This is our derivative. Now we got it simplified. Now remember, now as you go back here, now as you look at the derivative is slope. Right? So as you look at the derivative expression here, that represents our slope. And we're looking where the slope would be equal to 0, so where the derivative would be equal to 0. All right, so let's take the derivative, 2x over x squared plus 1 squared, set it equal to 0. And let's solve this for x now. As you solve for x, with our fraction here, let's multiply x squared plus 1 quantity squared to this fraction. You got to multiply x squared plus 1 quantity squared to the other side of your fraction. And let's see, this will give us 2x equals 0 or x equals 0. So the x value at this point is going to be 0. Now let's go back up to the original function. Now we're looking for the actual point, and let's take 0 and plug it into our original function to get our y value. So it does ask for the actual point. So substituting 0 in for x will give us 0 squared over 0 squared plus 1, which is 0. Right, so our y value, so x is 0, y is 0, so the actual point, we have a horizontal tangent line, it's going to be the point 0, 0. And there you got it. So just remember now, derivative is slope. So remember, in a horizontal tangent line, we would have a slope of 0. So you're talking about a flat line, slope of 0, that means the derivative has to be equal to 0 also. So once you get your derivative, that's your slope expression, set it equal to 0, solve for x. Let's try another one. Now let's see, this time we want to find differentiate without using the quotient rule. So let's try a couple of these problems here. I'll put a couple of them on my, just to kind of look at them. You know, the quotient rules, it's a kind of an involved, can be a long involved process. Lots of chances to miss the problem. So if you don't have to use the quotient rule, don't use it. So I'm going to look at a couple examples here. These are fractions, but they're fairly simple fractions that we can actually find the derivative without using the quotient rule. Now, if you like the quotient rule, you can use the quotient rule on every one of these and it will work. But most of these we can rewrite them so that we won't have to use the quotient rule. Now here we have x squared plus 3x over 6. Now to rewrite this so that we don't have to use the quotient rule, okay, let's divide 6 into each of these terms. Now this will be 1/6 x squared. Now 6x divided by 6 is plus 1/2 x. Okay, so divide both terms in your binomial by 6. Now we have like a little polynomial here, right? So to find our derivative, the derivative of 1/6 x squared, 2 times 6, or 2 times 1/6 gives us, so as you multiply 1/6 times 2, 2 over 1. This will reduce to 3, that'll reduce to 1, gives us 1/3. So this will be 1/3 x plus. Now the derivative of 1/2 x is 1/2, so you just drop the variable. And this is now our derivative. No quotient rule. Okay, that was a lot easier than using the quotient rule, but I guess the quotient rule will work on that one. Let's try this problem over here. Yes, we could use the quotient rule on this problem also, but let's see if we can simplify it enough to where we don't need to use the quotient rule. So first of all, let's multiply -3 inside our parentheses now. Y will be equal to, we'll make this -9x plus 6x squared divided by 7x. Now let's divide 7x into each of these terms. This will be negative 9x divided by 7x. It's a negative. And plus 6x squared divided by 7x. So divide 7x into both terms in your numerator. And now let's simplify them. So notice what happens. The x's cancel out. And that will give us -9/7 plus. And as we simplify now, this will be x squared divided by x, and we'll reduce to 1, and this will be just x, and this will be 6/7 x. Very easy to take the derivative of, right? So as you take the derivative now, y prime it should be equal to the derivative of -9/7. Now -9/7 is a constant. The derivative of any constant is 0, so this will be 0 plus. The derivative of 6/7 x is 6/7. So our derivative, y prime, is 6/7. Let's try another example. Let's look at this one here. There we go. Let's see, this time we have y equals 9/5x squared. All right, so 9/5x squared. Now let's see if we can rewrite this so that we don't need to use the quotient rule. Now, I said the quotient rule will work, but 9/5x squared is the same thing as 9/5 times 1 over x squared. Now, we know that 1 over x squared is what? X to the negative 2 power. So this is the same thing as y equals 9/5 x to the negative 2. Okay, now, let's use the power rule, not the quotient rule. As you get your derivative, negative 2 times 9/5 is negative 18 over 5 x to the, now you got to subtract 1 from your exponent, we'll make this to the negative 3 power. Now that's the general power rule. You take your exponent times your coefficient, and then subtract 1 from your exponent. And this gives us negative 18/5 x to the negative 3. Now I'm going to rewrite this without that negative exponent because I don't like negative exponents in my answer. So this will be negative 18 over, now the x to the negative 3 goes to the bottom of the fraction and with the 5. So it'll be 5x to the third power. That's our derivative here. Let's try another one. And we're quickly running through some of these. It says, prove that the derivative of tangent x equals secant squared x. All right. Now, on our previous video, I told us that the derivative of tangent x was secant squared x. Let's see why that's true. All right. Now, if you look at a function y equals tangent x, now tangent x is the same thing as sine x divided by cosine x. Let's use a quotient rule on sine x over cosine x, and let's see if we get secant squared x. That should be proof enough. So as we set this up in our derivative, and this would be cosine x squared, so the bottom squared, and then cosine x times the derivative of sine x. Well, I'm going to have to do this down here. So I can just extend my smartboard if I need to. So as we set this up, the derivative would be equal to, it would be cosine squared x in our denominator, and this would be cosine. So remember, the bottom times the derivative of the top. Now the derivative of sine x is cosine x minus, so the bottom times the derivative of the top minus the top, which is sine x, times the derivative of cosine. So the derivative of the bottom, derivative of cosine is negative sine. Right, so the bottom times the derivative of the top minus the top times the derivative of the bottom. Now we did with two negatives here, so I'm going to change that to plus a positive. And also cosine times cosine is cosine squared x. You have two negatives, and I'll make that plus. Now sine times sine is sine squared x. All this divided by 1. I'm sorry, all this divided by cosine x quantity squared. So cosine x quantity squared. All right. Now, also, you remember now, cosine squared x plus sine squared x, that's our Pythagorean identity, all right? So that'll simplify as 1 divided by cosine squared x. 1 over cosine is secant, so this is equivalent to secant squared x. So that's why you can just use the quotient rule to show that the derivative of tangent x is secant squared. So you end up with 1 over cosine squared x, which is secant squared x. Let's move on. Okay, let's take the derivative, get rid of that thing there, there we go. Okay, let's try to find the derivative of a trig function here. All right, now, this is what y equals x minus tangent x, as we take the derivative now. The derivative of x is 1 minus. Now we said the derivative of tangent x is secant squared x. So it'll be 1 minus secant squared x. That's it. Let's try another one. Okay, let's try this example right here. Get that off. There we go. Now this time you got to watch out. Now x secant x is a product. So x will be the first term. Secant x is the second term. All right, so we're going to use our product rule to find the derivative of x secant x. So we set this up. Our derivative, this will be the first. The derivative of secant, you remember, is secant tangent. So x, so the first time there is second. So I'm sorry, secant tangent. So the first time there is a second plus the second, which is secant x. And the derivative of x is 1. All right, so this is our derivative here. So it'll be x times the derivative of secant tangent, secant x tangent x plus, what should be secant x, I'm sorry, secant x times 1. There we go. Now, that's it. Now, the only thing we can do to this, we could factor secant x off. If you prefer the factored version, this would be secant x times x tangent x plus 1. So you can factor secant x off, but really that's it. You really don't have to put it in factored form unless you're told to do so, but that should be it. Okay, let's move on. And let's try this problem here. Now let's see, once again, another trig function. It's got secant and tangent in it. So as you take the derivative here, it should be pretty easy. You got to remember now the derivative of secant is secant tangent. So this will be 5 secant x tangent x. Now you'd be surprised, you know, for a lot of students the 5 will throw them off. But 5 is just a constant. So it's going to be 5 times the derivative of secant x, which is 5 times tangent secant. Now the derivative of tangent x is what? Secant squared x. It'll be plus secant squared x, and there you go. Now we can factor off secant again. So secant x times, that would be 5 tangent x plus secant x. Now, so if you put it in factored form, this is what the factored version will look like. Now, moving right along. Okay, let's try this one. It says we got f of x equals secant x. Find the equation of the tangent line at pi over 3, 2. All right, so this is a little bit different now. We're taking it a step further now, not just finding the derivative, but we're going to find the actual equation of our tangent line. All right, now that means now to get, we have the 1 point, pi over 3, 2. Right? We have 1 point on our graph. We need the slope. Now, the derivative is slope. So we're going to find the derivative, and then all we have to do is substitute pi over 3 in, and that will give us our slope. So to get started, let's find the derivative here first. Now this is f of x equals secant x. Now if you remember, the derivative of secant x is secant tangent. All right, so that's our derivative. So to get our slope, okay, at x equals pi over 3. Okay, you got to substitute pi over 3 into your derivative for x. And this will be secant pi over 3 times tangent pi over 3. Now, simplifying this is going to give us our slope, all right? Now, first of all, when I do secant and tangent, I'm going to rewrite these in terms of sine and cosine. It's a little bit easier to work with, so I'm going to do secant pi over 3 first. Now, secant is 1 over cosine, so it'll be 1 over cosine pi over 3 times. Now, tangent is sine over cosine, so this will be sine pi over 3 cosine pi over 3. Now, if you remember your unit circle, let me see if I can extend my page here a little bit. If you remember your unit circle, 1 over cosine pi over 3. Remember now, cosine, and the unit circle, pi over 3 is about right here. And I believe that is 1/2 square root of 3 over 2. And remember now, as you look at this point here, the first point is cosine. Okay, the y value is sine, right? So substituting 1/2 in for cosine pi over 3, this would be 1 over 1/2 times. Now sine pi over 3 would be the square root of 3 over 2 divided by cosine pi over 3 is 1/2. Now to get our slope, we have to simplify this expression. Now first, 1 over 1/2 is 2. Now remember now, times a fraction divided by another fraction. So when you divide fractions, so we're going to take the top fraction and multiply it by the reciprocal of the bottom fraction. So this would be 2, or 2 over 1, times the square root of 3 over 2 times the reciprocal of the bottom fraction, which is 2 again. So what happens? The 2's cancel out here, and that gives us the square root of 3 times 2, or 2 times the square root of 3. Now, this is our slope. So our slope is 2 square root of 3. Now, let's see if we can write our equation now. So erase this. So let's see if we can write our equation. And our equation would be y equals mx plus b. So I use our slope intercept form to write our equation. And let's see now, our point was, let me come up, was pi over 3, 2. Okay, so pi over 3 and 2. So let's take the 2, plug it in for y. That'll be equal to the slope, which we just got, which is 2 radical 3. So 2 square root of 3 times x. Let's see, times the x value, which is the square, which is pi over 3. Okay, plus b. So take the 2, plug it in for y, take the pi over 3, substitute it in for x. And we're going to solve this equation for b. Now remember, you always multiply the slope and your x value first. So it's going to be 2 equals. Now 2 radical 3 times pi over 3. Nothing really cancels, so this will be 2 pi square root of 3 over 3 plus b. So let's subtract this pi radical expression from both sides. We end up with 2 minus 2 pi square root of 3 over 3 equals b. Now that's our y-intercept. Now if you have a calculator, you can punch it up on your calculator, you get a decimal. But I'm going to leave it like this because it's not unusual if you ever take, students that are taking the AP Calculus exam, you may see this type of problem. It will be a non-calculator problem and you have to write your equation. So the equation here would be y equals the slope times x plus b, which is 2 minus 2 pi square root of 3 over 3. Now that's our equation. Now if you have a calculator, which I did this earlier, and what did I get for my slope? Okay, I got, well, if you have a calculator you can check it yourself, but just easy to put it in decimal form. Okay, let's move on though. Okay, let's try this problem here. Right. Now let's try some second derivatives now. Now, if you like doing the first derivative, second derivatives is twice the fun because you're going to take the derivative of the derivative now. So let's try this problem right here. It says we want to find the second derivative of this expression here. Now, first of all, I'm going to rewrite this. This is that little fraction, and this is x plus. So x plus, let's pull the 32 off, 32 times x to the negative 2 power. So 32 over x squared. Remember, I don't want to use the product rule on that unless I have to. That's just a little fraction. Pull that 32 off, be 32 times x to the negative 2 power. Now let's get our derivative. Now the first derivative, take the derivative of each term. Now the derivative of x is 1. Now take the derivative of 32x to the negative 2. Negative 2 times 32 is negative 64, x to the negative 3 power. So once again, remember you're going to subtract 1 from your exponent, multiply the exponent times your coefficient, subtract 1 from your exponent. This is the second derivative. Now let's find this is the first derivative. Now the second derivative is equal to, now take the derivative of each term. Now the way they see it, the derivative of 1 is 0. As you take the derivative of negative 64 x to the negative 3, we're going to do negative 3 times 64. Let me grab my calculator here, save a little bit of time. So 64 times 3 is 192. So be positive 192 x to the, now we're going to subtract 1 from our exponent again, be to the negative 4 power. That's the second derivative. Now remember, I don't like negative exponents, so I'm going to rewrite this as 192 over x to the positive 4 power. So that's our derivative here. Okay, let's try one more. So we'll try this one here. This may be our last one. I'm not for sure. We may have an application at the end, so we'll see. Now let's find the second derivative of this expression here. Now this is a square root. We have 6 times the square root of x to the 3rd power. And when I said about radicals, in calculus, a lot of times we want to convert from radical notation to rational exponent notation. So we don't want to work with the radical. We want to change it to, so we can see the exponents, so we can use the power rule. Now this is the same thing as, and this is a square root, so it has an index of 2. So this is the same thing as 6x to the 3 power. So you take your exponent divided by the index, so 6x to the 3 power. Now this is why, as we get our derivative, okay, the first derivative, you got to take your exponent times the coefficient. So 6 times 3 over 2, 2 reduced to 1, this reduced to 3, it gives us 9. So this would be 9x to the, now you got to subtract 1 from your exponent now. Now 3 over 2 minus 1, remember, is the same thing as 3 over 2 minus 2 over 2, which is 1/2. So it would be x to the 1/2 power. All right. Now that's the first derivative. Now to get the second derivative, we're going to do the same thing again. 1/2 times 9 is 9/2 x. Now you got to subtract 1 from your exponent. 1/2 minus 1 is negative 1/2. That's the second derivative now. So you find the second derivative just like you did the first. You just take the derivative of the derivative. So using the power rule 2 times here. Now let's see if we can rewrite this without the negative exponent. Erase that. So let's rewrite this. This would be, now Now see that x to the 1/2 will go to the bottom of the fraction, 9 stays on top, so it'll be 2x to the 1/2 power, or this will be 9 over, let's do the radical form also, this will be 1 over 2 square root of x. So x to the 1/2 is simply the square root of x, so either answer would be acceptable, I'm sure. Okay, and one more problem. Let's try this right here. Now, those of you, my students, you may have this in your guided notes. If I can, I'll try to put this in, but this is a little application. So the car is traveling at a rate of 66 feet per second. Okay, when the brakes are applied, the position function for the car is s of t equals negative 8.25 t squared plus 66t, where s is in feet, t is in seconds. So two things we got to get. One is the velocity and acceleration when t equals 3. So the velocity and the acceleration. T equals 3. Now this is our position function here. So let me bring that down here. So s of t equals negative 8.25 t squared plus 66t. All right. Remember now, velocity is the first derivative. Acceleration gives you the second derivative. All right. So let's get our first derivative, and then I'll get a substitute in for t. So let's do s prime t. All right, so the first derivative. Now you got to take the derivative of the position function. So as you take the derivative of negative 8.25 t squared, 2 times negative 8.25 gives us a negative 16.5 t. Subtract 1 from your exponent, so it'll be negative 16.5 t plus. Now the derivative of 66t is 66. You just drop the variable. So plus 66. All right, now let's see. So come on up here. Now we're looking for this is our velocity here. So this here describes our velocity. Right. Now, at t equals 3 seconds, let's substitute 3 in for t. So s prime at 3 would be negative 16.5 times 3 plus 66. And let me grab my calculator again. Okay, let's see what we get here. So it'll be negative 16.5. So negative 16.5 times 3, okay, plus 66. That'll give us positive 16.5. So 16.5. Now let's see, this is our velocity. So what was our units now? Feet per second. So it'll be 16.5 feet per second. All right, so that should be it right here. All right, so it'll be 16.5 feet per second. Now let's get the acceleration. Now to get the acceleration, let's come on down. You got to find this second derivative. Now the second derivative, s prime prime t. Now this is going to describe the acceleration of the, this will describe our acceleration. So the first derivative was negative 16.5 t plus 66. So taking the derivative of the first derivative, the derivative of negative 16.5 t is negative 16.5. Once again, you drop the t. The derivative of 66 is 0. So that's the acceleration. Now this will be in feet per second squared. Now the acceleration is constant everywhere. So at t equals 2, that's the acceleration. So we're done. Now, so we got our velocity is 16.5, and let's see, our acceleration was negative 16.5 feet per second squared. All right, and we'll stop here. Thank you for watching our video.